Bismillah ar-Rahman ar-Rahim. When we started the discussion of series, we said our target mainly is to discuss the convergence of series. Now let us recall this. An infinite series, we said it is a series written in this form that is n equal to 1 up to infinity, and then we have an. So that is just a1 plus a2 plus etc. This is up to, let us say, an, and this will move. We have infinite number of terms, and we need to know this will end up with a finite number, or it will not end up to a number, or the answer will be infinite. So meaning we need to know whether this is convergent or not convergent, and we defined what is the meaning of convergence. I will just recall this for you. That is, we need to define the sequence of partial sum. We give it the name Sn, where here n is equal to 1 up to infinity, and these Sn's are defined to be the partial sums. For example, Sn is just the addition from the first element a1, a2 up to an. So if we add only the first element, we call it the first partial sum. If we add the first and the second one, we call it second partial sum, and we throw them in a set, and that is will be called the sequence of partial sum. If the sequence of the partial sum convergent, then the series is convergent. So if the limit of Sn as n goes to infinity will tend up to a number S, a real number which is finite, then we say that the sequence of partial sum is convergent. In that case, we say the series itself is convergent, and the sum of the series is equal to S. This is what we have done before. Now, also we observe that if we try to find Sn, it's not always straightforward to rewrite it in a closed form, simple form, in order to evaluate the limit. Yes, we succeeded to do this in the geometric series. We did it for telescoping series, but not always an easy job. That's why we need to move to some alternative way to find convergence, or to test for convergence. One of these tests will be explained, is called the integral test. This test is taking advantage of whatever we have done before in the improper integral. So what is the title for this talk here? It is the integral test and estimates of sums. Integral test, we need to know what is the integral test, how to use it to test for convergence. And then after testing for convergence, someone will be interested in the sum. So if we cannot find the exact sum, we will move to the estimation. So we have another point, which is estimates of sums. So what is the integral test? The integral test says, okay, we are considering an infinite series, n equal to 1 up to infinity an. We suppose that we can define a function f, that is a function. This function agrees with the series at the points fn is equal to an, they are matching, and we need three properties now. We need this function to be continuous, positive, so we can apply it only if we have positive terms, and decreasing, 1, 2, 3. Continuous, positive, decreasing on the interval 1 to infinity. Then we can say that the series, the infinite series, is convergent if and only if the improper integral is convergent. Meaning, if the improper integral is convergent, the series is convergent. If the improper integral is divergent, the series is divergent. Okay, let us take a geometrical sketch of this test to just get an idea about what it means exactly here. Assume we have a function as mentioned in the test, a function with the nice properties, three properties here, just a typical one, for example, continuous, etc., decreasing, positive, so we are above the x-axis, and it is decreasing, positive, and continuous. So we have continuous, it is continuous, positive, okay, decreasing. So what is the relationship between improper integral and the series itself? Fine. Let's come to, let's say 1 here, partitioning this into 1, 2, 3, 4, etc. Okay? Now, according to the test, we have the assumptions of the test. We have the value of the function at each integer is equal to what? The images here, an. So at 1, the value here will be f of 1, and that will give me what? That will give me a1. Okay? At n equal to 2 or x equal to 2, again the image here is equal to f of 2, which is equal to what? Which is equal to A2. Because this function is f of x. Y equal to f of x. Okay? Fine. And so on. 3 will be f of 3 here, which is A3. F4 is, what's our target? Our target to discuss this sum. A1 plus A2 plus A3 plus A4 plus AN, etc. Okay, so what we will do, we will look at this in two different ways. Okay, the first one, I will form these rectangles. Look, at n equal to 1, I have this image here, which is f of 1, which is A1. So I will form this rectangle here. This rectangle now has a width equal to 1, and this is the height, which is A1. Fine. Going to the second one, I will form this rectangle like this. So it seems that I'm taking like what? I'm taking the right endpoints approximation. So this is at 3, this is the image here. At 4, this is it, exactly like this. Now let us ask the question, what are the areas here? What is the area of the first rectangle? What is the area of the second rectangle, third rectangle, etc. Okay, this is 1 times here the height A1. So this is exactly equal to A1. Yani. The area number 1 is exactly equal to A1. And the area number 2 is exactly equal to A2. This is 2 minus 1, which is 1 times A2, which is A2. And this is A3, and this is A4, and you move like this. What is our target here? Our target to find the sum from n equal to 1 up to infinity, an, that is the sum of A1 plus A2 plus A3 plus etc. And we are interested in this sum. Is it finite or not finite? And if you look carefully for the graph here, you can easily see that the sum of these areas will be less than the integral. Forget about the first one. If this is finite, let me write this one as A1 plus the remaining terms here. Okay? The remaining terms are just A2 plus A3 plus. So let us forget about the first one here. Comparing now the integral from 1 to infinity and the sum of these areas. Okay? That's what exactly the test says. So let us try to see that. Okay, fine. Now, coming back to the diagram we have here, we can easily see that the integral from 1 to infinity, f of x dx, this will give the area under the curve if it is there, if it is convergent. Okay? So 1 to infinity f of x dx. Now, which one is larger? The value of the integral from 1 to infinity f of x dx or the sum of these values? Clearly the sum of these values less than the total area from 1 to infinity. So this is always greater than or equal to what? Greater than or equal to the sum of these, so A2 plus, so I will say A1, A2 plus, A3 plus, A4, the infinite series starting from n equal to 2. I'm taking separately A1. Try to take an idea about the sum of these rectangles and the integral. Okay, fine. Of course, this is not our series. Our series, we need to add one more point, which is A1. Fine. But now, and these are greater than or equal to 0. Why? Because we have positive terms. Adding positive terms will be greater than or equal to 0. And we have non-negative function or positive function, so the integral actually is not greater than or equal to, even it is greater than 0. Now, let us look carefully here. Let us see the relationship between the integral and the series. Now, if this series here, is divergent, going to infinity, what can you say about the integral from 1 to infinity? We have done this comparison test before, and it says if this smaller one is going to infinity and these are positive values, so the larger one here also will go to what? To infinity. So the improper integral is divergent. Actually, we need the other way around. Now, if the integral here, which is larger than this, if this is convergent, what can you say about the sum? I mean, if this is finite, the largest one is finite, what can you say about the sum here? The sum here is finite. If the sum is finite here, adding one more finite term also will be finite. Meaning, in this case, if this integral is convergent, we can conclude that this is a finite number, adding a1 to it, so we end up with what? We end up with that the series itself is convergent. That is one point. Now let us look for the same graph in another way. I will sketch the same graph here. This is what we have. Okay, we have a nice function, continuous, positive, decreasing, etc. This is what we have, something like this. Okay, this is the x, y coordinate, and this is y equal to f of x. And we are trying to investigate the sum here, A1, sorry. This is 1, this is equal to 2, 3, 4, etc. And the images here are A1, the image here is A2, the image here is A3, and etc. The image here is A4. I will form different rectangles now. I will form these rectangles. Look, the value here is A1, and I will form this rectangle. Look, the second one will be like this. The third one also will be like this. Okay, fine. So what is this? This is A1, exactly, because this is 1 times A1. The area here is A2. The area here is A3. Now, summing these areas, comparing to with the integral from 1 to infinity. Of course, the sum of these areas now, the sum from n equal to 1 up to infinity of these ANs greater than equal to what? The integral from 1 to infinity f of x dx. So, now, both of them are greater than 0, positive. If this integral is divergent, if the integral is divergent, then for sure the summation is divergence. So we can use the benefit of improper integrals, which are easy to be evaluated, to get an idea about the series. In this case, if the integral is divergent, so this is divergent. In the previous one, if the integral is convergent, this one is convergent. So this is a geometrical point of view for the integral test. Now, how to use integral test to test some series for convergence? That will be our next point. Okay, before we go to the example, let us say something about the test. I will say that some series will start not from 1, from 3, for example, from 4. Then also it's enough to integrate from that number to infinity. Second one, if these properties are hold true from n to infinity, also that's enough to apply the integral test. Now let us see how to apply it. We have a question that says, test the series for convergence. Okay, so we need to ask ourselves, can we apply the integral test? The answer, if we can define a function that agrees with these points at the integer, with the sequence here. Second one, that function is supposed to be positive, continuous, decreasing on interval from n to infinity or 1 to infinity, then we can apply the test. Okay, let us see if we can do so. We have 1 over n squared plus 1, so we can define the function to be 1 over x squared plus 1. Now, let us check the requirements of the test. Is this function positive? Is it continuous? Is it decreasing? If the answer is yes, we will apply the test. Okay, and the test says this series is convergent if and only if the integral, improper integral from 1 to infinity of the function is convergent. Okay, let us see this. So, take a note of these things. First of all, clearly f of x is positive. Why? It's positive. Greater than 0. Okay, you have x squared, this is non-negative, adding 1, this is positive, positive divided by positive, that is positive. So the first one is there, it is positive. The second one we have, we need it to be continuous. Is f continuous here? If it's continuous, this is a rational function. This is a rational function, so it is continuous over its domain. And you can see here, this is continuous actually from minus infinity to infinity. Okay, so yes, we have continuous not only from 1 to infinity. We need it from 1 to infinity, but it's continuous in more than that. So it is continuous specifically from 1 to infinity. Okay, it's more than this. It's continuous for all interval minus infinity to infinity. Okay, the third one, is it decreasing? Is this one decreasing? Is the function f of x is decreasing from 1 to infinity? We need to check this one. So for decreasing part, we may use the derivative to justify our conclusion. So for decreasing part, what I will do, I will take the derivative of the function. You see that f prime of x here is, using the quotient rule, is minus 2x, the derivative of the denominator, over x squared plus 1 all squared. Clearly now, you can see that this is positive all the time. Minus 2x, it will be negative after 1, after 0, sorry, and positive before 0. So if we discuss the sign diagram of the derivative here, you have the critical point, which is 0. Then, clearly, if you check a point after 0, for example, 1, this will be negative. So this is negative. So it is decreasing actually after 0. And it is increasing before 0. So that is the sign diagram of the derivative. Okay, if the derivative is negative, it means the function is decreasing. If the derivative is positive, it means the function is increasing from minus infinity to 0. What we care about is this interval. So, do we have the requirements? The answer is yes. F is positive in that interval. F is continuous in that interval. Decreasing on that interval. So, it is decreasing from 0 to infinity. So, specifically from 1 to infinity, it is decreasing. So, all the requirements of the integral test is there. We can now move and apply the integral test. How to apply the integral test? Now, we consider now the improper integral. We consider the integral from what? From 1 to infinity, as the test says, and that is 1 over x squared plus 1 dx. Now, our job now is moved from testing a series for convergence to test an integral for convergence, and that is straightforward. How to test this one for convergence? We need to discuss the limit as t goes to infinity, whatever, call it t, p, whatever you like, 1 to t, and that is 1 over x squared plus 1 dx. We need to do the integration here. If this integral converge, the series will be convergent. If the integral is divergent, the series will be divergent. Okay, integrating 1 over x squared plus 1, that will give you tangent inverse of x, and you need to calculate this one from 1 to t, and that will give what? Limit as t goes to infinity, and I substitute by t, we have tangent inverse of t minus tangent inverse of 1, that is equal to pi over 4. Okay, fine. Now the question is, the limit here exists or not? Okay, tangent inverse is continuous, so we can take the limit inside. So t goes to infinity. If t goes to infinity, tangent inverse goes to what? Goes to, remember this graph of tangent inverse. Always keep it in mind. This is the tangent inverse here, something like this. This is y equal to pi over 2, and this is y equal to minus pi over 2. And the tangent inverse is an increasing function like this. It will go to what? It will go to pi over 2. So as t goes to infinity, actually this goes to pi over 2. So this is pi over 2 minus pi over 4, and that is equal to pi over 4. Now, what is the conclusion now? The limit exists. It means the integral is convergent. The integral is convergent. By the integral test, we have the series is convergent. So we'll say here, since the improper integral, the integral from 1 to infinity, 1 over x squared plus 1 dx is convergent, this implies the series we have, which is the series from n equal to 1 up to infinity, 1 over n squared plus 1 is convergent. By which test now? By, I will say, the integral test. The integral test. Okay, let me write it this way. By the integral test. So this is one application for the integral test. We have a series. That series contains positive terms. Continuous. If we can define a function that is continuous. Decreasing on 1 to infinity. So we take the advantage of improper integral in order to deduce something about convergence of the series. I just have a warning here. Maybe someone will confuse between the conclusion that it's convergent and between the sum. Nobody says that the sum is pi over 4. No. This pi over 4 just to conclude that the improper integral is convergent, but it has nothing to do with what? With the total sum of this. We have only a conclusion. Convergent, divergent. In this case, it is convergent. Now we will see another interesting problem about application for integral test. How to apply integral test in other examples. Now the second example we have is very interesting in the sense that it is discussing a very important type of series. Famous one. It's called the P series. Okay, we have a series like this. Summation from n equal to 1 to infinity, 1 over n to the power p. Is it convergent or not convergent? For what values of p will it be convergent, and for what values of p it will be divergent? That's the problem. Now, since p is free, we need to discuss cases, okay? So I will discuss different cases here. Case number one, let's call it like this. Case number one. What happened if this P is equal to 0? If the P is equal to 0, what do we have for AN here? If we substitute P equal to 0, then our AN will be exactly equal to 1. Okay? And if it is equal to 1, we know that the limit as n goes to infinity of AN is equal to the limit as n goes to infinity, it will be nothing but 1, and the answer is equal to 1. Now, from our previous talks, we said if the limit of AN is not equal to 0, for two reasons, either it's not equal to 0, a number not equal to 0, or it is infinite. In that case, if the limit equal to a number which is not equal to 0, the conclusion, this implies what? The series is divergent. The series is divergent. Okay? Now, which test says this? Divergent by what we call the nth term test of divergence. By divergence test, if you like. By divergence test. Others, they call it by the nth term test of divergence. Fine. That's the first case we have. Now, let us take another case for P. Case number 2. Now, what happened if we choose what? If we choose P to P, P to be what? To be negative, okay? Assuming P to be less than 0. Okay, what happened if P is less than 0? Say, for example, minus 3, minus 2. What can you say about the limit as n goes to infinity of the nth term? What is the limit of the nth term? It is 1 over x to the power, 1 over n to the power p, n to the power what? N to the power p. Now, you should be careful here. P is negative. Let us say minus 2, minus 3, minus 1/2, etc. And you are taking n goes to infinity. So this value will be what? If this is negative, you can take it up. N to the power minus p will be positive, and n will go to what? N will go to, the value will go to infinity. So this is equal to infinity. Okay? Just take a simple example. If p is negative, it means a sample of that you take, for example, 1 over n to the power minus 2. When you take it in the numerator, that will be the limit as n goes to infinity of n squared, and clearly this will be what? Infinity. In general, if p is negative, the limit of this will go to what? Infinity. So what is the conclusion? The conclusion, so the series, in this case, the series is divergent. Okay, who says this? Who says that the series is divergent? The answer, it is divergent by, again, what we call the divergence test. The divergence test says, if you remember, it says if the limit of AN is not equal to 0 or does not exist, the series is divergent. That's exactly what we have. Now, the interesting case is the third case. What happened if P is positive? Now, the last case we have is if P is positive, what's happening here? Now, this is very interesting case. If P is positive, let's define a function first. So let f of x be equal to 1 over x to the power p. Now, let us check the requirements of the integral test. Okay, this function here we have, number 1, f is, okay, the first one, it is positive on this interval 1 to infinity. Okay, why it is positive in 1 to infinity? Because if you just substitute positive number, you raise it to a positive exponent, that is positive, 1 over positive. So this is the condition is true here. The second one, this function is continuous on this interval, 1 to infinity. Why this is continuous in 1 to infinity? First, because it is a rational function, so it is continuous over its domain. And you can see now, the function here is not continuous only at the point x equal to 0. We are taking care of that because we are taking only the interval from 1 to infinity. So it is continuous 1 to infinity. What it remains now is just to check number 3, that is the decreasing. Is f decreasing on 1 to infinity? This is what we need to check. Decreasing on 1 to infinity. Okay, why it is decreasing on 1 to infinity? Let us justify this. Now it remains to check the decreasing behavior here. Is the function f is decreasing on 1 to infinity? Let us check this one. We have f of x is equal to x to the power minus b. I just rewrite it this way. It is 1 over x to the power p, so I will say it is x to the power minus p. So this implies f prime of x is equal to minus p, okay, minus p, x to the power minus p minus 1. So you can rewrite this one as what? Minus p divided by x to the power 1 plus p. Fine. Look now for the quantity here. You can see that this is if for 1 to infinity. I'm talking about 1 to infinity. This is positive. 1 plus p is positive. So this is positive quantity. P itself is positive, multiplied by minus. So this is always less than 0 for all x between 1 to infinity. This is always negative. So if the derivative is negative, so the function is decreasing. So all requirements we need is there. Okay, fine. What is the conclusion now? The conclusion is this. The integral test says this series given by n equal to 1 up to infinity. I'm talking about the third case we have here. This is 1 over n to the power p is convergent. If and only if, let us write it this way, if and only if, the improper integral from 1 to infinity, 1 over x to the power p dx is convergent. Okay, but if you remember when we discussed the improper integral, this was one of the examples we did. And we said this improper integral is convergent only if p is strictly greater than 1. If p is strictly greater than 1, then this improper integral is convergent. So the conclusion, the improper integral is convergent for the choice of p to be strictly greater than 1. This implies by the integral test we have what? The series. They call it P series, okay? The P series is convergent if P is strictly greater than 1. Fine. Now what is the conclusion now? We started this example, which is the series of 1 over n to the power p. We found that for p greater equal to 0, this is divergent. For p equal to something less than 0, it is divergent. For p positive between 0 and 1, it is also divergent. But for p greater than 1, it is convergent. So let us write the conclusion. This series n equal to 1 up to infinity, 1 over n to the power p, which is called p series, is convergent if what? P is greater than 1, and not only this, divergent if we have P is less than or equal to 1. So this will add now a very famous type of series. By looking, we can answer the question whether it is convergent or divergent, and we will see this in the following example. Now let us see a direct application of the example we did now. Yeah, we have a series or set of series. We said test each of the following series for convergence. Now quickly we can answer the questions because we have a result here. Okay, the integral of, the series from 1 to infinity, 1 over n cubed. The series from 1 to infinity, 1 over n cubed. Now we just need to remember the shape of the P series. The shape of the P series always is something like this. We have n equal to 1 up to infinity, 1 over n to the power p, and we have a nice result that says if p is greater than 1, strictly greater than 1, this is convergent, otherwise it is divergent. Let us apply the test now. Okay, our P here is equal to 3. So this series is convergent. Why? This series is convergent. What is the justification for this? We can either apply the integral test or we take the benefit of the previous example. So this series is convergent. We say it is P series. It is P series with what? With P equal to 3, and that is strictly greater than 1. So that's enough to say it's convergent because we have a result about the P series. Similarly, you can do for this. This series is divergent. This series, okay, this series is divergent. Why it is divergent? Again, the justification because it is P series, okay, with P is equal to 1/3, and that is strictly less than 1, so it is divergent. Okay, what about the last one here? 1 over n to the power pi over 3. 1 over n to the power pi over 3. The only thing we care about is the value of the exponent here, if it is less than 1 or greater than 1. Okay, pi is 3.14 something, approximately equal to 3.14 something. If you divide by 3, so you have a number greater than 3, divide by 3, so that is what? That's greater than 1. That's the only thing we need to test here. So this is convergent. This is convergent P series with what? With P is equal to pi over 3, and we need to write this is greater than 1. And since it is greater than 1, so it is a P series with P greater than 1, so the conclusion, it is convergent. Okay. In the 2 or 3 examples we did here, we have the function is continuous, positive, decreasing from 1 to infinity. And we said this is not always possible. Sometimes you have functions that are very nice, positive, continuous, but maybe not decreasing from 1 to infinity. It may start to be decreasing from 3 to infinity. Okay, that's fine. It's not a big deal. We can also apply the integral test, and the following example will illustrate this point for us. Okay, what is the example? The example here says, test the series given by this, which is n equal to 1 up to infinity, and we have the logarithm of n, ln of n, all over n for convergence. So is it convergent or divergent? Is it convergent or divergent? Test this one for convergence. Okay, that's it. How to test for convergence? We need to ask, can we apply the integral test? Can we apply the integral test? It means we need to answer the questions here. Can we define a function that agrees with the sequence at the point of integers? Is this function positive, continuous, decreasing? If yes, we can apply the integral test. Let us see this. Okay, we can apply a function, and that function easy to be integrated. That is ln of x all over x. Now observe the following. Okay, is this function positive? Is this function positive? Let us see this. From 1 to infinity, this is positive. The logarithmic function, if you just remember, it has this shape. We have the logarithmic function is something like this. This is y equal to ln of x. Okay, this is the xy coordinate. This is exactly at x equal to 1. So yes, after 1, this is positive. We have no problem. So f of x is, okay, it's greater than equal to 0. Let's say greater than 0 for all x, for x inside this interval 1 to infinity. So that's okay, fine. The second point, this is positive. Is it continuous? F of x is continuous. Why it's continuous? Okay, it is the quotient of 2 continuous functions, ln of x and x. From 1 to infinity, we have no problem here because this is continuous over its domain. So it is continuous from 0 to infinity. And this is continuous all the time. And we need to ignore the zeros of the denominator, so which is only 0. So, okay, it is continuous on this interval 1 to infinity, if you like. Fine. Is it decreasing? We need to check if it is decreasing from 1 to infinity, or from certain number n positive integer up to infinity. For the third one, decreasing. Again, we will use the tool of derivative to check this. So how to check this one for decreasing? I will find the derivative, f prime of x. What is f prime of x? It is the derivative of the logarithmic function that is equal to 1 over x times the second one, which is x here, minus ln of x multiplied by the derivative of x that is equal to 1, all divided by what? X squared. Fine. But this is equal to what? X will be cancelled with x here. So we have 1 minus ln of x all over x squared. Okay, for x greater than 1, for x is positive. This is always positive x squared, because x is positive, so x squared is positive. So the only thing that affects the sign diagram of the derivative function is 1 minus ln of x. Okay, let us ask the question here. 1 minus ln of x. We need it to be negative, right? Why? Because we need the function to be decreasing. So we need to see when this is negative, when it is positive. This is less than 0. Okay? Implies ln of x greater than 1. And this implies x must be greater than e to the power 1. Because this is increasing function, so you can take e to both sides. E to the power ln of x greater than e to the power 1, and the exponential is increasing. So x greater than 1 will give us this quantity is negative. This quantity is negative, it means the derivative is negative here. So what is the conclusion? We can see that at e, after e, the derivative here, f prime, it will be negative here, positive here. Okay, fine. So the function is decreasing after e, but not starting from 1. E is approximately 2.7 something. So let us see if we can apply the integral test. The integral test requires the function to be positive. It is positive, no problem. F is continuous, okay, fine. Decreasing, but it's not decreasing from 1 to infinity. It's not a big deal. All these properties, meaning the function is positive, continuous, decreasing, starting from what? Let us take the next integer. For example, here what? 3. So we have the function f is what? 1. Positive, let us write it this way. Second one, continuous, we have no problem. The third one, it is decreasing on what? 3 to infinity. Is it enough? Yes, it is enough. If you can prove that this function is positive, decreasing, etc. on a specific interval from n positive integer up to infinity, you can still apply the integral test. Now, the integral test says this series will be convergent if the integral from 1 to infinity of the function ln of x over x is convergent. Let us see if we can find the answer by using the improper integral. Okay. We apply the integral test. We apply the integral test. So, in that case, we consider the integral from 1 to infinity ln of x divided by x dx. Okay? Ln of x over x dx. How to evaluate this? We need to take the limit as t goes to infinity. Okay, let us take enough space here to find the answer and then find the conclusion. To find the improper integral there, we need to find the limit. We consider this limit as t goes to infinity. And that is the integral from 1 to t. And we have here ln of x divided by x dx. And clearly this is equal to the limit as t goes to infinity. Okay, you have the function over times its derivative. So that is just ln of x all squared divided by 2, evaluated from 1 to t, and you can see that this is equal to the limit as t goes to infinity of ln of t all squared over 2, minus at 1, that's equal to 0. Now what is the limit as t goes to infinity of ln of t? This is infinity. When you square it, it will go to infinity. So the final answer here is infinity. The conclusion is, since the limit of this is equal to infinity, it means this integral is divergent. And if the integral is divergent, by the integral test, the series itself is divergence. Let me write this one for you. Okay. So this implies the integral from 1 to infinity ln of x over x dx is divergent. Okay, if it is divergent, the conclusion, then this implies by the integral test, the series given by n equal to 1 up to infinity, that is ln of n over n is also what is divergent. So that is another example where we applied the integral test and we reached the conclusion. But in this example, we are relaxing the requirements to have it to be there from a finite number, a positive integer to infinity instead of 1 to infinity. Now, maybe someone will say, okay, we end up with the conclusion. So what? If you end up that the series is divergent, that's it. Divergent makes no sense. We have no value for the sum. But if it is convergent, can we find the sum? In most cases, in series, many cases, you cannot find the exact sum. If you cannot find the exact sum, what should we do? We move to the second option, to estimate the sum. So the question now, if we apply the integral test, and we conclude that the series is convergent, how to estimate the sum? That will be our next point. Now, let us assume that we have a series and we concluded that this series is convergent. The question is, can we estimate the sum? Okay. And if we estimate the sum, what will be the error involved? Let's go back to the series. We have n equal to 1 to infinity. Assume we have a series that is satisfying all requirements of the integral test. Now, let's open this. Let's expand it. You have a1 plus a2 plus a3 plus, let us say, an. Then we have an plus 1 plus an plus 2 plus, etc. an plus 3. And this will move to up to infinity. Fine. If we conclude that this series is convergent, then always we can estimate the sum. How to estimate the sum? Okay, you have infinitely many ways to estimate the sum. You can stop at the first point, and you say that the summation here is approximately equal to the first partial sum, a1. You can stop at the second point, and you say, I'm just taking the 2 points, a1 plus a2, so I'm taking only the second partial sum. In that case, we can always say, okay, S here is approximately equal to what? It's equal to A1. In this case, this is S. Let us write it this way. Approximately is equal to S1, and S1 is exactly equal to A1. Let's write it this way to see what will be the error here. This is S1, and this is equal to A1. Now, if you are only taking the first element, what are the terms you are missing here? The terms that you are missing is called the error in that estimation. So in this case, if you take only the first element, all of these will be your error. So in that case, we have S is approximately equal to S1. In that case, R1, the error involved by taking only the first element is equal to what? The summation A2 plus A3 plus A4 plus etc. This is the error involved. You can estimate the sum by taking only the first 2 elements is 2. So that is what? A1 plus A2. Now the question, what will be the error involved in this estimation, R2? What is it equal to? What is the error? If you are taking only the first and the second element, your error will be A3 plus A4 plus. Okay, so this is A3 plus A4 plus. Fine. In general, if you estimate S by taking only the first n elements, so that is equal to A1 plus A2 plus until you reach AN. You stop at AN. What is the error involved here? The error involved will be called Rn, and Rn is starting from what? From the next term, an plus 1 plus an plus 2 plus. Now we need to have an idea how large is the error, because all the time we are shooting for a certain accuracy. Depending on our accuracy, we need to add certain number of terms. Okay, maybe someone will be interested to find the error to be less than 0.1. Another one, no, he needs to be less than 0.001, more accurate, or 0.0001, and etc. So all the time you change your accuracy, you need to know how many terms you need to add so that you have this accuracy. Okay. Now we conclude this by summarizing the error involved in such calculation. I will clarify it by geometrical explanation. Here, the estimating the sum of a series. Assume we have a series like this, where the integral test is applicable, meaning we can define a function, that function is decreasing, positive, etc. The all requirements there. And we know that this series is convergent to S, so S here is finite number. Then you can always estimate S by taking partial sums. But in that case, you'll have the error involved will be greater than or equal to the integral from n plus 1 to infinity, f of x dx, and less than the integral from n to infinity, f of x dx. How to see this? Okay, let's consider the function we have. Okay, I will graph this. This is like a function which is decreasing, etc., continuous, positive. This is y equal to f of x. And this is the x, y, etc. And what we are trying to do here is to have an idea about this summation here, the error involved. So the error involved in taking Sn is an plus 1, an plus 2, etc. Okay, if you just imagine what's happening here. Assume this is, after some points, this is called n. So this will be what? N plus 1. So what is the image here? The image here is an plus what? Plus 1. Okay? And then, if you take this is n plus 2, n plus 3, etc. So this point is n plus 2. This point is an plus 3. This is an plus 2. This is an plus 3. Okay, fine. I repeat, we are interested in these values here. An plus 1, an plus 2, an plus 3, etc. Okay, fine. If you just take the images like this, if you take the image here, and up to this point here, up to an plus 1, and form this rectangle here, forming this rectangle. What is the area of this rectangle? It is n plus 1 minus n, that is 1, multiplied by n plus 1, so this is an plus 1. Okay, fine. Taking the image here, forming this rectangle, this is n plus 2 minus n plus 1, that's 1, multiplied by n plus 2, so this is an plus 2. And etc. You just form a third one here, this is an plus 3, and so on. Now let's compare, look, we are comparing the integral from n to infinity with this summation. Okay, the integral from n to infinity will give me the area under the curve. So what can you say about the integral and this summation? Clearly this summation here, an plus 1, so let us say like this, n equal to, this is ai, I is equal to, which is actually, let's write it as our error, Rn. Rn is the summation, an plus 1, an plus 2, an plus 3, etc. You can easily see that this is less than or equal to the integral from n to infinity f of x dx, from the shape we have in the front. So that's exactly what we have here. That's one point. I will graph the same shape again. So this is what we have. This is, okay, I'm graphing a decreasing function, positive, etc. This is continuous, x, y. This is y equal to f of x. I'm again trying to get an idea about if you have terms like this. This is n plus 1, this is n plus 2, this is n plus 3, and so on. This is n plus 4, etc. Okay? Now, if we just form this one, this rectangle like this, what is the area of this rectangle? The rectangle here is has a width equal to 1, and the image here is an plus 1, so this is an plus 1. And the area of the second rectangle I will form like this. This is an plus 2. And you move like this, an plus 3, an plus 4, an plus 5, etc. So what can you say now about the integral from n plus 1 up to infinity, which is the area under the curve, and the summation of these rectangles? Which one is larger? Of course, the areas of these rectangles are larger. So in that case, we can see that Rn, the error involved in adding only the first n elements in the series, will be greater than or equal to what? The integral from n plus 1 up to infinity f of x dx. And that's exactly what is written here. So this is more interesting here. If you just look for this part of the inequality, this always will give you an upper bound for the error. Of course, this will give you a lower bound for the error. And most likely we are interested in finding how large is our error. In that case, this will indicate for us how many terms we need to add to have a certain accuracy. We will see this one in the following exercise. Okay, let us see an application for this estimation theorem we have. It says the question says approximate the sum of the series by using the first 10 terms. And then we need to estimate the error in this approximation. Fine. So to estimate the sum, it means S is approximately equal to S10. What is the meaning of S10? It means we are adding the first 10 terms only of the series. So that is equal to what? We substitute, we have 1 over 1 cube plus 1 over 2 cube plus 1 over 3 cube plus until we reach what? 1 over 10 cubed. Now if you use a calculator, this will be approximately equal to what? You just add these numbers, you'll have the sum is approximately equal to 1.1975. Okay, so we are approximating by taking only the first 10 terms. The question is, what is the error involved in this approximation? Meaning, how large is R10? R10, we need to find R10, the error corresponding to adding only the first 10 elements. According to the theorem we have here, it says the error is less than or equal to the integral from n to infinity f of x dx. What is f of x? F of x is the function that matches with this sequence, so it is 1 over x cubed. So in our case, this is less than or equal to the integral from 10 to infinity, and that is f of x 1 over x cubed dx. Okay, you need to calculate this integral. That will give us, of course it will give us a finite number because the series is convergent. So this is convergent for sure. Okay, so let's calculate this integral now. How to calculate the integral? We need to go back to the definition of improper integral. Now we know that this is convergent, so we can directly say that this is equal to the limit as t goes to infinity, okay? And we just remove that infinity to t to be t, and we integrate x to the power minus 3 dx. Fine. If you integrate, this will be equal to, okay, the limit as t goes to infinity, and we have x to the power minus 2 over minus 2. So it is minus 1 over 2 x to the power 2, if you like. Okay? X to the power minus 3 plus 1, that is x to the power minus 2 over minus 2. So that's exactly what we have. And then we have this one from 10 to what? To t. If you just simplify, this is the limit as t goes to infinity. And if you replace t here, you have minus 1 over 2t squared minus minus, that's plus 1 over what? 1 over 2 times 10 squared. Okay, I leave it like this before I continue. As t now goes to infinity, this quantity goes to what? This goes to 0. So what is the final answer? It will be 1 over 2 10 squared. 10 squared is 100. 100 by 2 is 200. So it is 1 over 200. If you multiply by 5, that will be 5 over 1,000. So it is 0.005. That's the answer. Just, you can check this one easily. Now, that's the first part. If we are adding 10 terms, we expect to have an error which is less than 0.005. So that's fine. So it seems this series is convergent and a little bit fast, okay? Because 10 terms will give us a good accuracy. The second question is another important problem in application is this. Before we start, how many terms we need to add or require to have the sum of the series with the absolute value error to be less than 0.005. I guess this we have 3 zeros instead of 2 zeros. Yeah, we have, otherwise we are back to the same question here. This is 0.005, something like this. Okay, so we need more accuracy. If we are looking for 0.005, 10 terms enough to have 0.005. We need to have it 0.0005, 5 out of 10,000. So before we go and start, how do we know how many terms we need to add? Same formula will give us the answer. But again, we are using this relationship here. If we need the error to be less than that number, 0.0005, and we know that the error is less than this integral or equal to, so we need to force this integral to be less than that number. If we force this integral to be less than that number, then we are sure that our error is also less than that number. That's exactly what we need to do. Okay, so I need to do this. To have the number of terms, I need to force. I know that Rn is less than or equal to this, which is n to infinity, 1 or f of x dx. I need this one to be less than this number, 0.0005. So what should I do? I replace this by its value, n to infinity. F of x is 1 over x cubed dx. I need this one to be less than 0.0005. Now, if you look for this integral, we will repeat the same procedure here. But if we take the advantage of this part, what's happening here if we replace 10 by n? And we move parallel to this. At the end, we have 1 over 2n squared. Instead of 10, I have n squared. So I leave it for you to justify that this will give us 1 over. I am using the same argument here. So I will end up with 2n squared. And we need this one to be less than. That is 5 over 10,000, something like this. Okay? And then we need to find the number of n here. N is equal to what? So if we take the reciprocals, this will be, okay, simplifying here, maybe you can have 1 over 2,000. That's one thing here. Taking reciprocals, dividing by 2, so we have n squared must be greater than 2,000 divided by 2, that is 1,000. So your n is supposed to be greater than square root of 1,000, which is equal to 10 radical 10, something like this. And this is approximately, if you find it by a calculator, it will be around 31 point something. So that is, yeah, it is 31.6. This is what I found. Now, if we say, in order to have the error in the estimation to be less than this number, we need to add numbers of terms to be greater than 31.6. Of course, number of terms should be integer and greater than 31.6. So what is the minimum? How many terms we need to add? So what is the minimum number of terms? The minimum number of terms need to be added so that the sum will be accurate up to that error is 32. So we need to add, let us say, at least 32 terms. That's the answer for the question here. Fine. One more point. Let's go back to this exactly, this, argument we are doing here. I will modify it a little bit. Look. Always, if we have a convergent series, then the sum of the series will be equal to what? A1 plus A2 plus AN plus 1 plus AN plus 2 plus etc. Okay. If we say we will estimate it by adding the first n terms, we call this one what? Sn. For each Sn, there is a corresponding error called Rn. This is your Rn here. So always, the sum, the exact sum now, the exact sum is equal to any estimation Sn plus its corresponding error Rn. Fine. Look for this inequality here. We have an idea about what? About Rn in terms of the integral. What happened if I add Sn to Rn? What happened in that case? We gain a very interesting result. Look here. If we add Rn to Sn, I am adding Sn here for all sides. Here, here, here. What do you get? Rn plus Sn will give me the sum. The exact sum now. Greater than, equal to, less than, equal to. I repeat this. I have Sn plus Rn is equal to the sum. So this is less than equal to Sn plus the integral from n to infinity f of x dx. Okay? And now this is greater than equal to the n plus 1 up to infinity f of x dx plus Sn. So once you find the partial sum to the error, you end up with an estimate of the sum. I mean the exact sum. You can find a bound, an upper bound, lower bound for the exact sum. You can always estimate. You can always study the how much is your error. I mean how large is your error, how small is your error. And also you can find a bound for the exact sum by using integrals. And that will conclude the section by the last point here we did. And I will give you a specific exercise, continuation of the exercise we did, to have an idea about this inequality here at the end for the exact sum. Now, you remember we said we are approximating using how much? 10 terms. So we end up with what we call the 10th partial sum as an estimate. And we end up with R10, that is 0.005. I commented these results before I move to the last point. You see, when we add only 10 terms, this is the error involved. When we need to have more accuracy, more terms need to be added here. So we added 32 terms instead of what? Of 10 terms. I move now to the last point. With n equal to 10, can you find how large is the exact sum and how small is the exact sum? And this will be our last point here. Okay, this is like a remark. If we add only 10 terms, if we are adding only 10 terms with n equal to, so that this is the remark we have at the end. With n equal to 10, with n equal to 10, so let us take the advantage of our calculation here. With n equal to 10, we know that the sum, now the exact sum, is bounded between what and what? This is bounded between, okay, according to what I wrote there, it is S10 plus R10, which is what? Which is n to infinity. This is n to infinity. R10 is bounded between these two things. F of x dx, and larger than S10 plus the integral from n plus 1 up to infinity, what? F of x dx. Now, calculating this, you have s greater than equal to, less than equal to. We have this result, S10, which is 1.1975. And we know this is not n anymore, this is 10, and this is what? 10 plus 1, that's equal to what? That's equal to 11 here. And we know the result of this. The result of this is clearly, we have it here. It is 1 over 2 times 10 squared. There is the same, it is 1.1975 plus 1 over 2 times, this will be 11 squared. And you can calculate this, so you have s is less than equal to, greater than equal to. The final answer will be something like this, 1.2025532, and this is 1.201664. So, what is the conclusion now? We started this section discussing a series, a specific type of series, that is a series where you can define a function, matching with a series at the integers. This series is supposed to be with positive terms. The function defined is supposed to be decreasing from 1 to infinity, or at least from some integer to infinity, positive integer, and continuous. Then, we were able to deduce convergence of the series by using the improper integrals. And at the end, we were able to estimate the sum of the series by using integrals. And finally, we have a nice results that give us our exact sum between what and what. And you see this is very nice result here because you are adding, you have an idea now about the exact sum between two numbers that are close to each other. So almost you are there, almost you have the exact sum, but as an estimate. That's why we call it integral test and estimating sums. That is the end of integral test.